This video is not sponsored by anyone, but I want to start with something that sounds almost like a trick. You've heard it your whole life. The speed of light is a constant, exactly 299,792,458 meters per second. That number is etched into physics textbooks, repeated in documentaries, printed on posters, and even used as a trivia question.
Curious about how the world really works? Not the myths, not the shortcuts, the real science behind everything we see and experience. On this channel, we explore mind-bending physics, unravel the secrets of the universe, and uncover the hidden patterns that shape our reality. If that excites you, subscribe for weekly deep dives into science and discovery. Hit like and share with friends. Your curiosity drives our next adventure. Leave a comment and let us know what puzzles we should solve together.
We're so confident about it that since 1983, humanity has defined the meter itself based on the speed of light. A meter is officially the distance light travels in a vacuum in 299,792,458ths of a second. So the speed of light isn't just some measured fact, it's part of our very definition of reality. That seems airtight. Case closed, right? Except there's a strange twist hiding in plain sight. Because here's the claim I want to make in this video. No one has ever actually measured the speed of light. Not in the way we think. Not in the way you measure the speed of a car, a baseball, or even sound waves through the air. And I'm going to prove to you that we can't. Not with any experiment that's ever been done. Not with the most precise technology we have today, and maybe not ever. Sound like clickbait? It's not. By the end of this, you'll see why the number we all know as the speed of light is something stranger than a measurement. It's a definition, a convention, maybe even an illusion. Let's start simple. How do you measure speed? It doesn't matter if it's a sprinter, a baseball, or a car. You need just two things: distance and time. Speed is distance divided by time. Imagine I fire a baseball out of a cannon. I set up 2 points a few meters apart. I run a high-speed camera. The ball leaves point A at 1 frame, reaches point B a few frames later, and I count the difference. Distance over time, that's my speed. Simple, intuitive, reliable. Now imagine trying the same with light. Take a perfect vacuum tube, exactly 1 kilometer long. At one end, I fire a laser beam. At the other end, I place a detector. All I need to do is start a clock when the light leaves and stop it when the light arrives. Right? Well, here's the problem. The moment the light reaches the detector at the far end, I have to know instantly that it got there. But if my clock is back at the laser, how do I know what happened 1 kilometer away without waiting for another signal to return? Okay, new plan. Put one clock at the laser and another clock at the detector. Synchronize them so they tick in perfect unison. Then when the laser fires, the detector can stop the second clock at the exact instant the light arrives. Now I have distance and time. But, hold on. How do you synchronize 2 clocks that are separated by a kilometer? You could send a signal from one to the other, but that signal itself travels at the speed of light. So, you'd need to know the speed of light in order to synchronize the clocks. But synchronizing the clocks is what you need in order to measure the speed of light. That's a trap, a loop you can't escape. You might say, fine, just sync the clocks while they're sitting together, then physically carry one down to the far end. Problem solved. Except it's not. Because as soon as you start moving the clock, relativity comes into play. A moving clock ticks differently than a stationary one. By the time it arrives, it's no longer perfectly synchronized. This is where the neat trick of using 2 clocks breaks down. Every attempt to measure light's one-way speed runs into this paradox. To measure it, you need synchronized clocks. But to synchronize clocks, you need to already know light's one-way speed. So, what do? You cheat. You get rid of the second clock entirely. Put a mirror at the far end of your 1-kilometer tube, fire the laser, let it bounce off the mirror and return to you. Now you only need a single clock at the start. The light leaves, makes the full round trip, and you time the whole journey. That's measurable. That's how physicists have always done it. And that brings us to a French physicist in the 19th century, Hippolyte Fizeau, who pulled off the first real measurement of light speed.
Covering Fizeau's experiment and how we've always only measured the round-trip speed of light. Back in 1849, Hippolyte Fizeau set up one of the most elegant experiments in physics. He placed a bright light source behind a rapidly spinning gear with hundreds of teeth. The light passed through a gap in the gear, traveled about 8 kilometers to a distant mirror on a hill, bounced back, and then had to pass through the gear again to be seen by the observer. By adjusting the speed of the spinning gear, Fizeau could find the precise rotation rate where the returning light was blocked by a tooth instead of slipping through a gap. From the geometry, the distance, and the timing, he calculated the speed of light to be about 313,000 kilometers per second. That was astonishingly close, within just 5% of the value we accept today. Later, other scientists refined the method. Armand Fizeau, Léon Foucault, Albert Michelson, they all devised clever ways to bounce light off mirrors, spin wheels, rotate prisms, and time the round trip. By the late 1800s, Michelson had narrowed it down to within a few hundred meters per second. And over the decades, technology made these measurements more and more precise. Lasers, interferometers, ultra-stable clocks, every new tool confirmed the same result. Light speed in a vacuum is c. So, hasn't the speed of light been measured? Well, not exactly. What Fizeau and everyone after him really measured was the two-way speed of light, the time it takes for light to travel to a point and back. And the two-way speed is always going to come out as c, no matter what. Here's the twist. We have never measured the one-way speed of light, from point A to point B, just the outbound trip. And maybe we never can, because hidden in all those mirror and bounce experiments is a subtle assumption that light travels at the same speed in both directions, forward and back, symmetrical. But what if it doesn't? What if light is slower going out and instantaneous coming back? Or vice versa? What if the speed in one direction is half of c, and in the other direction, it's infinite? Here's the uncomfortable truth. The experiments we've done so far cannot tell the difference. So here's the puzzle. What if the speed of light in one direction is different from the speed in the opposite direction? Say, it crawls at half of c on the way out, and then instantly zips back on the return. From Earth, we'd never notice, because when we do our mirror and back experiments, the average speed over the full round trip still comes out as c. Take a simple thought experiment. Imagine sending a radio signal to an astronaut stranded on Mars. We send, "Hello, are you there?" And 20 minutes later, we get the reply, "Yes, I am." So naturally, we assume 10 minutes for the signal to get there, 10 minutes for it to come back. But what if reality is stranger? What if our signal actually took the full 20 minutes to crawl its way out, and the astronaut's reply snapped back instantaneously? From our perspective, the timeline looks identical. There's no way to tell those two scenarios apart. That's the essence of the one-way speed problem. We can measure the round-trip speed perfectly, but the one-way speed, the speed in a single direction, is unmeasurable without already knowing it in advance. Because to measure a one-way trip, you need synchronized clocks at both ends. And the only way to synchronize them is to already assume something about the speed of light. It's a catch-22, a perfect loop. Physicists call this the conventionality of simultaneity. And it means the statement, "the speed of light is the same in all directions," is not an experimentally proven fact. It's a convention, a choice we've all agreed to use. Einstein himself admitted this right in his 1905 paper that launched special relativity. He wrote, carefully in italics, that the assumption of equal light speed in opposite directions was done by definition. By definition, not by experiment, not by proof, by choice. And that choice underpins everything we know about relativity, simultaneity, and the way space-time is stitched together. Einstein in 1905 laid the foundation of special relativity, but before he even touched on time dilation or length contraction, he spent the first couple of pages wrestling with a deceptively simple question. How do you synchronize two clocks in different locations? He called the clocks A and B. If you're standing at A, how can you be sure that B shows the same now as you? Einstein proposed this method. Send a light pulse from A to B. When B receives it, it immediately sends a reply back to A. If the round trip takes, say, 10 microseconds, then you define that it took 5 microseconds each way. So when B got the signal, you say it was exactly halfway through the total time. That's the Einstein synchronization convention. And notice the key word, convention. He didn't say, we know this is true. He said, let's agree to make it true by definition. That's wild, because it means simultaneity. What counts as happening at the same time in two different places is not discovered by experiment. It's stipulated. It's chosen. So when we say the speed of light is the same in all directions, what we really mean is we've decided to define it that way so our physics works cleanly. But nothing prevents us from choosing a different convention. For instance, we could define that light takes all the time on the way out and none on the way back, or that it's slower in one direction, faster in the other. All of these choices are mathematically consistent, as long as the round-trip speed still comes out to C. And physics doesn't break. That's the mind-bending part. The laws of relativity, electromagnetism, quantum mechanics, they all still hold up no matter what you choose as your one-way speed convention. Einstein simply picked the neatest, simplest version: symmetry. Light goes the same speed both ways. It was a brilliant choice, but it was still a choice. And here's the kicker. Over a century later, no experiment has ever been able to prove otherwise.
Where we dive into why every attempt to measure the one-way speed of light ends up collapsing back into the same paradox. Scientists, of course, have tried. For over 100 years, clever minds have asked, isn't there some trick to get around the clock synchronization problem? What if we used a single clock? Maybe place a clock at the source, send a photon, and when it reaches the detector, instantly trigger a signal back along a wire to stop the clock. That way, you'd think you're only using one clock. Sounds good, right? But here's the snag. How fast does that electrical signal travel through the wire? To know that, you need to calibrate it. And how do you calibrate it? By comparing to the speed of light. So you've smuggled the very assumption you were trying to test back into the experiment. Okay, maybe use rotating setups like Fizeau's spinning cogwheel or Michelson's mirrors. But all of those rely on light going out and coming back. They always collapse into a two-way measurement. Even modern experiments with lasers, GPS satellites, and atomic clocks hit the same wall. The moment you try to pin down the one-way trip, you find yourself relying on some convention of simultaneity. It's like trying to measure the speed of a car when your only ruler is painted on the car's windshield. Every method loops back on itself. And physicists know this. That's why in the literature, the one-way speed of light is often described as conventional. It's not that it doesn't exist, it's that we can't, even in principle, measure it without already assuming it. In other words, the experiment can't escape the circle. Where we connect this ambiguity to relativity and why the universe still works just fine. At this point, you might be thinking, wait, if we can't measure the one-way speed of light, doesn't that break physics? Doesn't it make relativity meaningless? Surprisingly, no. In fact, it makes relativity even more elegant. Einstein theory doesn't need the one-way speed to be really equal in all directions. It only needs the round-trip speed to be constant. And that's the one thing experiments confirm again and again, to mind-bending precision. Think about GPS. Your phone can tell you where you are within a couple of meters by syncing up with satellites orbiting 20,000 kilometers above Earth. The system relies on signals traveling at sea. And it works, only because the round-trip consistency is rock solid. Whether light really took 67% of the time going up and 33% coming down, doesn't matter. The math cancels it out. Physics shrugs and says, pick whatever convention you like. I'll still give you the right answer. That's the beauty. Relativity is flexible enough to survive the ambiguity. But this flexibility also forces us to confront a deeper question. Is the speed of light a fact of nature, like the mass of an electron, or is it more like a rule of language that we invented to make sense of things? Because the way we've built the system, c isn't just a measurement. It's the yardstick we've chosen to measure everything else. And when the yardstick itself is part of the definition, you stop being able to ask what its true length is. That's why physicists sometimes describe the one-way speed of light as not an empirical matter, but a convention. Reality doesn't care how we slice it. The universe just keeps working. So here's the paradox we've lived with for over a century. We know the speed of light. We use it to define our units, run our technology, and build our physics. But in another sense, we don't know it at all. The one-way speed of light isn't a discovery. It's a choice, a convention that makes the universe intelligible. And maybe that's the real lesson. Not everything in science is about uncovering hidden facts. Sometimes it's about choosing the cleanest, simplest framework that lets the laws of nature reveal themselves. Light remains the fastest thing in the universe, but the way we measure that speed reminds us even the most solid numbers can rest on a foundation of human agreement. And that's why after all this time, no one has ever truly measured the speed of light.